Hello and welcome back. Mr. Johnson with you. And in this video, we are going to be looking at predicting products and specifically for single and double replacement reactions, or what can also be referred to as single and double displacement reactions. And if you've been with me for the previous two video series, you already know that this is a little bit different of a setup. So I do apologize in advance. If the audio seems a little weird, or if there's a glare on the board and you're not able to read something that I'm putting up here. But moving on forward, talking about single and double replacement reactions. Again, these are two of the 5 types of chemical reactions that we can see within chemistry. Those 5 types, again, being synthesis, decomposition, combustion, which are the concepts that I've covered in 2 previous videos, and now single displacement and double displacement, or again, single or double replacement. So jumping into this, go on and talk about what exactly is a single displacement reaction. Well, when we look at a single displacement reaction, this is where you're going to have an individual element reacting with the compound. And that lone element is going to displace or replace an element of like charge within the compound. And by like charge, what we mean is a positive atom will replace a positive atom. A negative atom will replace a negative atom. And again, while I'm saying atoms, we always have to think about reactions in terms of ions. Okay? Because when we look at single replacement reactions, these occur in what's called an aqueous solution. And aqueous means that we've taken a solid, for example, sodium chloride or table salt, put it into water, and it dissolves. Well, another term that we use in chemistry is dissociate, or it dissociates. Sounds very similar to disassociation. In other words, they break their association. And when I put something like sodium chloride into water and it dissolves or dissociates, what I'm going to have is sodium ion floating around and chlorine ion floating around. Now, if I introduce another element into that and that element is soluble, then what ends up happening is it's going to have ions, and now it can float around. And if it's a positive ion, when it bumps into the negative ion that's in solution because of the compound that's dissolved, that new positive and that original negative can pair up and produce a new substance. Okay? So when we look at the general reaction, you'll notice that it's A plus BX yields AX plus B. Well, in that case, if we go to the board with this, and I mimic what is there in the notes, A plus BX, I'm so used to writing an element symbol, BX yields, to get the products that they're showing for this, A is positive, and then my compound, again, as I stated in the previous 2 videos, we're dealing with ionic compounds. So the first component is positive, second component is going to be that negative charge. So when I look at this, if this is an aqueous solution, which you would see a little AQ written in parentheses for the phase of that substance. But what's going to happen is A is going to come over and it's going to replace component B, or it's going to displace it over onto the product side. Then I'm going to have A with its positive charge now able to combine with X with its negative charge, which A can be +1, +2, +3. X can be, again, 1 negative, 2 negative, 3 negative. So these are just generic charges. And again, A and B do not have to have the same numerical value of charge. It's simply that they're both positive. So what ends up happening is AX combine, and that's my new compound. Conversely, the other reaction shows this idea of Y plus BX yields BY plus X. Well, in that case, I'm trying to remember what the reaction was again. Sorry, y plus bx, losing my mind, y'all. Y plus bx yields. Well, in this case, to get the compound of by, y would have to be my negative. B is still positive, x is negative. And now y is going to come over and displace or replace x. So x ends up on its own. And then I'm going to have b as my positive component, y is my negative. And again, this could be a 1 positive, 2 positive, 3 positive, 4 positive. The transition metal, which we haven't dealt with, but that is also viable. Then it could have, positive 4, positive 5, positive 7, depending on the transition metal. And then y is going to be my negative 1, 2 negative, 3 negative, possibly 4 negative. And again, that's how I end up producing my other substance of By. Okay? So when we are looking at this, typically what we have is the replacement of a metal with another metal. Okay? This, the negative replacing can happen, but typically when we're seeing single displacement or single replacement reactions, it's a metal replacing a metal. Okay? But I will show you an example of a negative replacing a negative, or a non-metal replacing a non-metal. Now, in this is where it gets a little hairy, because when we are looking at single displacement reactions, we have to take into account this thing called the activity series. And the activity series tells me which elements actually have the ability to replace or displace other elements. Okay? So when we look at the activity series, this is the ability for an element to react with another element. Okay? And the greater the reactivity, typically the greater the activity. And when it comes to metals, we base their reactivity and therefore activity on their ability to lose electrons. Well, their ability to lose electrons, or the energy required to remove electrons, that's ionization energy. So typically, not always, but typically, the lower the ionization energy of a metal, the more reactive that metal is, and therefore higher on the activity series. Non-metals, on the other hand, we base their reactivity off of how easily they are able to gain electrons. That's electron affinity. And likewise, the greater the electron affinity, the greater the ability for that non-metal to gain electrons, and therefore the greater its reactivity or activity. So one of the guiding principles is for reactivity or activity is that an element can only displace elements that are below it on the periodic table. So if I'm looking at a reaction where I have, say, lithium in a compound, and I introduce sodium to that reaction mixture, because sodium is below lithium, sodium's not going to be able to replace lithium because lithium is more reactive. But if I reverse that and I have sodium, the less active within the compound, and I can put lithium into solution, because lithium is higher on the periodic table and therefore has a higher activity, it can displace that sodium. So we have to look at these reactivity series. Same thing, we look over at nonmetals. If you look at column 17, the halogens, fluorine is the most active. So it can replace chlorine, bromine, iodine, astatine out of compounds, but none of those can displace fluorine out. Chlorine cannot displace fluorine, but chlorine can displace bromine and iodine. So again, anything that's underneath it on the periodic table, typically it can displace or replace. So let's go and take a look at a couple of examples of single displacement reactions, and then we'll look at our double displacement reactions. Okay. So for single displacement reactions, clear this board. If I have a reaction, for example, where I am taking, let's do lead sulfate. So PbSO4, coming up with these off the top of my head. And so this is my compound, and I introduce to this, say, chlorine. Okay? So I'm going to show you that example of the negative displacing. So chlorine within a compound would be the negative charge. Lead is my positive. Sulfate is my negative. So one of the possibilities would be that chlorine would come over and displace my sulfate, would then give me my sulfate ion, which is 2 negative. And then I would have lead, which in this case would be a 2 positive. Chlorine as that 1 negative. And we always want to write it positive and then negative. And then we'd cross down our charges to get subscripts. And I would get PbCl2. So this is what we'd predict. However, we would have to check the activity series to see if chlorine is actually capable of removing the sulfate from that lead. If so, this is what we expect from the reaction. If we find out that chlorine is lower on the activity series than sulfate, then instead of these products, we get no reaction. Okay? So this is where that activity series comes in. Let's take a look at another one. Let's take a look at if I have lead and I combine that with magnesium chloride. So will lead be able to displace magnesium? And the reason we look at lead and magnesium is because lead is positive, magnesium would be positive, chlorine would be negative. So as a result, lead would come in and displace magnesium. So magnesium goes from being in a compound to being by itself. And now I would have lead, which in this example, we're just going to take lead to be a positive 2 or a 2 positive. And it's going to combine with chlorine as a 1 negative, crossover charges, Pb1Cl2. So lead 2 chloride is my new compound. And again, we'd have to look at activity series. If lead is more active than magnesium, then this is what we would predict for the products. If, however, lead is less active than magnesium, then this would be a no reaction. Okay? So let's look at one more single displacement. If I take chlorine gas and I combine it with potassium bromide. Okay? So again, chlorine would be my negative, potassium positive, bromine negative. So chlorine is going to look to displace bromine. So this again is activity series. And on the periodic table, we can see very clear that chlorine is higher in the column than bromine. So chlorine can indeed displace bromine. So as a result, bromine becomes our individual product. And if you're wondering why I put the Br2, because bromine again is one of those diatomic elements. Anytime that bromine ends up by itself, it's always with the subscript of 2, similar to chlorine, which is a diatomic. So now for my new compound, I'm going to take that potassium, which would be a 1 positive charge. And we find that 1 positive by looking at the column heading. Combine it with chlorine, which is a 1 negative. Cross down those charges, and I get KCl as my new compound. So this is what we'd predict for the reaction. Okay? The reverse of this, just to give you this idea, if I now took bromine and tried to react with potassium chloride, bromine being negative, chlorine being negative, bromine would want to try to displace chlorine, but because bromine is lower on the periodic table, it can't. And as I was saying earlier, this is no reaction. Nothing's going to happen because bromine is less active than chlorine. So only more active elements can displace less active elements. Less active elements cannot displace more active elements. So that is single replacement or single displacement. So now let's turn our attention to double displacement or double replacement. And when we look at double replacement reactions, this is where you take two compounds, typically they are metal containing compounds, and we put these into solution and they switch out partners. The positive replaces the positive. You could also look at it as the negative replaces the negative. Either way, you'll get the same result. But when we run a double displacement or a double replacement, typically we're going to end up producing either a precipitate, which is a solid product. We're going to produce an insoluble gas, so we'll see bubbles of something leaving the reaction mixture, or we're going to end up producing water. Okay? So when we look at double displacement reactions, we've got this general reaction of AX plus BY yields BX plus AY. Okay? So what we're doing is we're switching out those positive components between the two substances. Okay? So let's go on and take a look at double displacement and how this works. Starting out with the generic, and instead of using A, B, and X and Y, I'm going to do this another way that you might see in books, and that is AB plus CD. Okay? So a lot of textbooks will just use A, B, C, and D. Okay? But A is positive, B is negative, C is positive, D is negative. Because again, in a compound, it's always the positive component, then the negative component. So I can look at it as A comes over and it displaces element C, but element C can come over and replace element A. So as a result, when I get my products, what I'm going to have is A as a positive combining with D as a negative, and I will have C as a positive combining with B as a negative. So as a result, I get compounds AD and CB. So this is switching out the positives, but here's what I want you to notice. If I switch out the negatives, instead I looked at it from the viewpoint of B is going to displace D. D would come around and, would replace B. So as a result, I would still have C combining with B. B is my positive, C is my negative. Right? Let's put that backwards. Sorry. C is my positive, B as my negative. So I'm still going to get CB. And I'm still going to have A as my positive combining with D as a negative to form AD. So you can either look at it as a switching out of the positive components or switching out of the negative components. Either way, you'll get the same results. So let's actually take a look at a reaction that is double displacement. So if I take, say, potassium iodide, and I combine potassium iodide with lead nitrate, PbNO3, 2, so lead 2 nitrate. So again, I always go through and I label my positives and negatives so I can see what's going to switch out. So potassium will replace or displace lead. Lead will come over and take the place of potassium. So what this leaves me with is potassium, which would be a 1 positive charge, now combining with that nitrate, NO3, as a 1 negative. And I would have lead as a 2 positive, because that 2 crosses back up, combining with iodine as a 1 negative. So crossing down charges, 1 and 1. So my first product would be potassium nitrate. And my second product, when I cross down those charges, would be PbI2, my lead 2 iodide. So this is double displacement. And in this, what we'd find is PbI2, this is our precipitate. It would fall out of solution, hence we call it precipitate. It's like rain, precipitation. We would see that solid form and eventually it would settle at the bottom of the test tube or the beaker or whatever reaction vessel we're using. Potassium nitrate, on the other hand, this actually remains soluble. So even though we write it down as potassium nitrate forming, the reality is potassium ion and nitrate ion, when they bump into each other, they're more stable remaining ions than what they are forming a compound. So as a result, they bump into each other and then decide, no, we don't want to form a compound. Lead and iodine, on the other hand, when they bump into each other, forming that ionic bond lowers their energy, and hence the ionic bond forms. And when it forms, you get a solid product or a precipitate. So let's take a look at another one. So another double displacement reaction. This would be iron 2 sulfide. So FeS, it's my iron 2 sulfide. And I'm going to react this with hydrochloric acid, so HCl. So again, if you want to, like I normally do, I go on and put the positive and negatives on there just as a remembering, or some people are perfectly fine with just saying the first component of each of the two compounds, these are going to switch out. They're going to replace each other. So when that happens, I'll end up with Fe as a 2 positive, now combining with chlorine as a 1 negative. And when I cross down those charges, my first product, it will be FeCl2, so iron 2 chloride. My other product would be hydrogen as the positive, combining with sulfur, which sulfur is a 2 negative. So when I cross down, H2S, and this is an example of an insoluble gas forming. H2S would be a gas that forms, right? So this again, double displacement. I'm taking my first components, my positive components, and I'm switching them out. And notice the charges do not have to be equal. It's not a positive 2 can only replace a positive 2, or a positive 1 can only replace a positive 1. It's simply that the positive replaces the positive. So final example of a double displacement reaction. And this is where I'm going to take HCl, or hydrochloric acid, and react it with sodium hydroxide. This is actually not just a double displacement, but an acid-base reaction. Okay? You go on into advanced sciences, what you'll learn is that the 5 general types of reactions, synthesis, decomposition, combustion, and then single displacement and double displacement, what this video is on, they actually fall into 3 categories: precipitation reactions, acid-base reactions, and what's called redox reactions, or oxidation reduction. Okay? So this is an acid-base reaction that follows the criteria of a double displacement. And in it, again, we're going to take and we're going to switch out those first components. So what I'm going to have is hydrogen as a 1 positive, now combining with OH as a 1 negative. I'm going to have Na as a 1 positive, combining with my chlorine, Cl, as a 1 negative. And when we cross down charges on each one of these to get our formulas for our products, we get NaCl and H2O. So this is a double displacement that results in the formation of water. Okay? So again, single displacement, double displacement, probably some of the easier types of reactions to predict products for, okay? Because you are just switching things out. Combustion is probably the easiest. Single displacement, double displacement, a close second. So I hope this video has made sense to you. If you have any questions, you have any comments, or you have ideas for future videos, please let me know. I'd love to hear from you. As always, thanks and take care.